Welcome dear students. Uh, in this video today we will be discussing about our first scheduling algorithm, that is first come first serve. As far as this algorithm is concerned, it is one of the simplest algorithms amongst all the scheduling algorithms, and the principle behind the working of this algorithm is that the process which requests the CPU first is allocated the CPU first. That means, let's suppose we are having a ready queue where number of processes are waiting for the allocation of CPU. Let's suppose those processes are P1, P2 and P3, and they have put their request in the order of, that is, P1 has put his request first, thereafter P2 came and had put its request for CPU's time, and thereafter P3 came and has put his request for CPU's time. So the order in which they have arrived, accordingly the CPU's allocation will be done to these processes. That is, first of all P1 will get the access of CPU, then P2 will get the access of CPU, and then P3 will be getting the access of CPU. So a first in first out queue is maintained in this approach, and it is one of the simplest scheduling algorithms, as I've already told you. And one more thing about this algorithm is that it works in a non-preemptive manner, which means that once the process is allocated the CPU, it will continue its working with the CPU, or it will be continuing accessing the CPU for the entire burst time. Let's suppose the burst time of a process is 5 milliseconds. For this process the burst time is 10 milliseconds. For third process the burst time is, let's suppose, 7 milliseconds. So once P1 has gained the access of CPU, it will keep on working with CPU for 5 milliseconds. In between, this process cannot be removed from running. That is, a higher priority process cannot come in between, and in a scenario that this process has to leave the control of CPU in the middle so that the new process can gain the access of CPU. So that is why I'm saying it works only in non-preemptive manner. So how its working takes place, let's take one scenario where we'll be discussing in a numerical way out that how the working of this FCFS algorithm takes place. Let's assume that we are having three processes over here. For example, we are having the first process, that is P1, then there is P2, and then there is P3. So in this numerical, for each of the processes we are having their burst time. That is, P1 needs CPU for 24 milliseconds, P2 needs CPU for 3 milliseconds, and P3 needs CPU again for 3 milliseconds. And we are assuming that these processes basically have arrived, let's suppose, at the same time. As I've told you, their arrival times have been 0, 0 and 0. Now question arises, who will get the access of CPU in such a scenario? In that case, the order in which the processes are there in the table will work accordingly. So our aim over here is to calculate the average waiting time. So to get the completion time, we need to prepare a Gantt chart for these set of values. So as far as Gantt chart is concerned, this is how we can formulate a Gantt chart. For example, initially the process P1 came at time 0. Fine. So once P1 came over there, it got the access of CPU. So P1 is now having the access of CPU and is executing, and it continues there for how much milliseconds? It continues there for 24 milliseconds. So from 0 to 24 milliseconds, it is the P1 who is continuing. Then the question arises, who came next? So we are assuming that the order in which these processes are shown in this table, accordingly we will be going on with the following the same order, because arrival times were same. So thereafter P2 came. So P2 came, I mean to say P2 got the access of CPU. So P2 got the access of CPU at 24 milliseconds, and it will continue there for 3 milliseconds because its burst time is 3. So that means from 24 till next 3 milliseconds, that is till 27. For 3 milliseconds P2 continues, and thereafter what happens, the P3, when P3 got the access of CPU, so accordingly when P3 gets the access of CPU, it continues there for 3 milliseconds. So that means from 27 till 30 the control of CPU was with process P3. So this is how we can prepare the Gantt chart. As far as these FCFS or other remaining algorithms are concerned, for each of those cases, first of all we need to prepare the Gantt chart of that scenario given in the question, and thereafter we can compute its completion, its completion time. So if you see over here, turnaround time is completion time minus arrival time. As far as completion time of P1 is concerned, P1 began at 0 and it completed at 24 milliseconds. So that means 24 is CT minus arrival time. Arrival time was 0. So in this case, the turnaround time for P1 comes out to be 24 only. Thereafter, if we see the completion time of P2, P2 completed its job at 27. So CT of P2 is 27, means completion time is 27, arrival time is 0. So we got 27 as its turnaround time. Then comes P3. P3 completed its job at 30th millisecond. So 30 minus arrival time is 0. So in this case, the turnaround time is 30. To calculate the average waiting time of processes, those two values are of turnaround time as well as burst time. The turnaround time for process P1 is 24 and the burst time of process P1 is 24. So I mean to say 24 minus 24, and we get the value of process P1's waiting time as 0. Then about P2's turnaround time is 27 and its burst time is 3. So 27 minus 3, so we get the value as 4. If we move to the process P3, so in this scenario the turnaround time of the process is 30, fine, and the burst time for P3 was 3. So the waiting time for process P3 is 27. So the next, as far as the question was concerned, we were supposed to calculate the average turnaround time as well as the average waiting time. So to get the average turnaround time, first of all we'll add the average turnaround, the turnaround time for each of the processes. In this case we are having total 3 processes. So first of all we need to add these values, that is 24 plus 27 plus 30. This divided by the number of processes that were in the system. So as of now we were having 3 processes only. So once we do this calculation, we'll be able to get the value of average turnaround time in this scenario. So if we add up these 3 values, this comes out to be then it comes out to be 81, I believe, if I'm not wrong, while adding the values divided by 3. So this means that the average turnaround time for these set of processes is 27 milliseconds. Fine. The next thing was we were supposed to calculate the average waiting time. The average waiting time for this scenario will be 0 for process P1, then 24 for process P2, then 27 for process P3, divided by total number of processes. So 0, 24 and 27. I'm adding these 3. I got the value as 51 in this case upon 3. That means the average waiting time is 17 millisecond if we are working on such a system. And we are aware about this thing, that it is better if the waiting time is low. The more better is the system. Fine. We need to have a minimal waiting time, then only we can consider that the algorithm was efficient. So let's move on to the next part. So in the current problem shown in front of you, we are having 5 processes over here, and again we are supposed to calculate the average waiting time for this system. So there is one difference between this problem as well as the previous problem, and that difference lies in the arrival time. In the previous scenario, I mean to say in the previous slide, we were having three processes and all of them arrived at time t is equal to 0. That is, the arrival time for all the processes was same. But over here, the arrival time of different processes is different. If you see, P0 arrives at time 2, again P1 arrives at time 2, but P2 arrives at time t is equal to 0, P3 arrives at time t is equal to 4, and P4 arrives at time t is equal to 3. So the question arises, how can we resolve such an issue and get average waiting time for such a system? So the very first thing over here is that we are supposed to prepare the Gantt chart for this so that we can get the completion times of various processes. So let's have a look on the Gantt chart which we'll be preparing based upon this scenario. If you see over here, it is P2 which came at time t is equal to 0. So obviously P2 came first, so P2 will be allocated the CPU initially. So it came at time t0. Its burst time was only 1 millisecond, so it accessed CPU for 1 millisecond. So at 1 millisecond, if you see over here, uh, there was no other process available in the ready queue. In fact, the next processes came at time t is equal to 2. That is, P0 also came at time t is equal to 2, and P1 also came at time t is equal to 2. Other processes, that is P3 and P4, they came even beyond that. So at time t is equal to 1, there is no process which is waiting in the ready queue. So when there is no process, it means in such a scenario, the CPU will be idle. So the CPU is idle at this time. For how many milliseconds? Because at t is equal to 2, the next process arrived. So during this phase, your CPU was idle. Fine. So at this time, the CPU is idle. So now we were having two processes available in the system at time t is equal to 2. So just like previous scenario, as I've told you, the process which is in the table which is shown first, we are taking that into consideration first. So we are taking P0 over here first. So P0 needs uh, 7 milliseconds of CPU's time. So that means from t is equal to 2 till next 7 milliseconds, that is till 9, P0 is executing. Thereafter P1 is executing, and P1 executes there for 9 milliseconds. That means from 9 till 18 it is P1 which is having the access of CPU. So thereafter it is P4 which enters the system prior to P3. So we are handing over the control of CPU with P3, sorry, with P4. So P4 executes first, and it executes there for next 3 milliseconds, that is from 18 till 21. And at last it is P3 which will be executing. So it executes there for next 5 milliseconds, that means from 21 till 26. So this is the Gantt chart of this scenario. So let's see the completion times of various processes. If we observe over here, P0 completes at time t is equal to 9. So completion time of P0 is 9. For P1, the completion time is 18. For P2, the completion time is 1. For P3, the completion time is 26. Process P4's completion time is 21. So accordingly, if you see over here, we can now calculate the turnaround time, and turnaround time is completion time minus arrival time. So completion time is 9 for P0 and arrival time is 2. So that means 9 minus 2. This comes out to be 7. Then for P1 it is 18 minus 2. This comes out to be 16. Then for process P2 it is 1 minus 0, as P2 came at arrival times with arrival time 0, so it is 1 minus 0, so we get 1. Then completion time of P3 is 26 and its arrival time is 4. that is this one. So 26 minus 4, this comes out to be 22, followed by P4, where the completion time is 21 and the arrival time is 3. So 21 minus 3, this comes out to be 18. So now let's calculate the waiting time, which is turnaround time minus burst time. So these are the turnaround times for various processes, that is 7, 16, 1, 22 and 18 for process P0, P1, P2, P3 and P4 respectively. So waiting time is turnaround time minus burst time. So this comes out to be 7 minus burst time of P0 is 7. The burst time of P0 is again 7. So 7 minus 7, this comes out to be 0. For P1, the turnaround time is 16 minus burst time is 9. So this comes out to be 7. Then the completion time for process P2 is 1. Its arrival time was its burst time was 1, that is this one. So 1 minus 1, this comes out to be 0. The completion time of P3 is 22 minus its burst time is 5, this comes out to be 17. Then for P4 we are having 18 minus 3, so this comes out to be 21. So the next step is to calculate the average turnaround time as well as the average waiting time. So if we go for calculating the average turnaround time, so it comes out to be, we have to add 7 plus 16 plus 1 plus 22 plus 18. So if we add all these values, this comes out to be I believe this comes out to be 64, that is 7 plus 16 plus 1 plus 22 plus 18, that is I'm adding all the values of the turnaround times, these values. And because the number of processes in the system, total number of processes are 5 in number, that is from P0 till P4, so dividing by 5, this comes out to be 64 by 5. So the turnaround time comes out to be 12.8 milliseconds. The next thing which we were supposed to calculate was average waiting time. So average waiting time, again we first of all need to calculate the waiting time. We need to fetch the waiting times of all the processes individually and then add all those and divide by total number of processes. So the waiting times of different processes are 0 plus 7, then again 0, then 17, and then the last one was having 21 plus 21 and divided by 5. So this comes out to be 38 plus uh, sorry, this is 20. If I see over here, it is, just a minute, I've put a wrong value over here. It was not 15, but it was supposed to be, it was not 21, it just needs to be 15. So I've fetched the wrong value. Kindly make the corrections. 18 minus 3 is 15, so plus 15. So 17 plus 15 plus 7, this comes out to be 39. So 39 divided by 5, fine, and 39 by 5, so this comes out to be 7.8 milliseconds, which is the waiting time for the system shown in front of you. So now let's take another issue which is there with regard to first come first serve. So let's move on to the next slide for discussing that issue, that is convoy effect. So let's consider a scenario where we are having one CPU bound process and many IO bound processes. Suppose that is the case. Though in this example in the table, I'm only having two processes, and there is one CPU bound process, that is P0 in this table, and then we are having only one IO bound process, that is P1. So let's see what is the impact of this scenario while we are calculating the average waiting time. So first of all, let's draw the Gantt chart for this system. And if we draw the Gantt chart for this scenario, we are having only two processes. So it is P0 which came first. So it begins its execution with the CPU, and it executes for 100 milliseconds, and thereafter P1 gains the control of CPU, and it executes for next 2 milliseconds, that is from 100 till 102. So the completion time for P0 is 100. So I'm putting 100 over here in the completion part, and the completion time for P1 is 102. Fine. Now let's calculate the turnaround time. The turnaround time is completion time minus arrival time. Completion time is 100, arrival time is 0. So 100 minus 0 comes out to be 0 for process P0. Whereas for process P1, the completion time is 102, whereas arrival time is 1. So 102 minus 1, this comes out to be 101. Similarly, let's calculate the waiting time for process P0 and P1. So waiting time is turnaround time minus burst time. So turnaround time for process P0 is 100, whereas burst time is 100. So 100 minus 100, again this comes out to be 0. Then if you see over here, for process P1, similarly turnaround time is 101, whereas burst time is 2. So 101 minus 2, this comes out to be 99. So if we calculate the average turnaround time for uh, this system, so this comes out to be 100 plus 101. So that means 100 plus 101 is 201. So 201 upon how many processes are there? So there are two processes. So turnaround time comes out to be 100.5 milliseconds. Fine. So if we calculate the average waiting time for this system, the average waiting time is uh, sum of the averages of individual processes, that is 0 plus 99. So this comes out to be 99, and we are having two processes divided by 2, so this comes out to be 49.5 milliseconds. So let's just have the another option over here, and we have made only one change in this table. We have simply gone for a scenario where we are assuming that process P1 comes first instead of process P0. That is, now we are saying that first of all the IO bound process uh, gets the access of CPU, and thereafter the CPU bound process gets the access of CPU. And what is the impact of such a scenario on this system? Again, let's prepare the Gantt chart of this system. So because again we are having two processes, so P1 comes first, it executes for 2 milliseconds, it comes at time 0, executes for 2 milliseconds. Thereafter P0 comes, P0 gets the control of CPU, it executes for 100 milliseconds, it begins at 2, ends at 102, and this is the Gantt chart for this system. Now let's calculate the completion time. Completion time for P0 is 102, whereas the completion time of P1 is 2. Let's calculate turnaround time. Turnaround time is 102 minus arrival time, that is 1. So this comes out to be 101 for process P0, whereas for process P1 it is 2 minus 0. This comes out to be 2. Fine. Similarly, the waiting time for process P0 is 101 minus the burst time, that is 100. So this comes out to be 1, whereas in this scenario this comes out to be 2 minus burst time 2, that is 0. Fine. So again, if we calculate the average turnaround time, so this comes out to be 101 plus 2, that is 101 plus 2 is 103 divided by 2. Fine. And this comes out to be 51.5 milliseconds, whereas if we go for the average waiting time for this system, the average waiting time is 1 plus 0 and divided by 2, so this comes out to be 0.5 milliseconds. Now just compare the waiting times, the average waiting times for both these scenarios. Over here the average waiting time is 49.5, whereas the average waiting time over here is 0.5. We were having same two processes, but only the order of accessing the CPU was changed. So why this is happening? This is happening because of the convoy effect. Fine. So if what the convoy effect says, it says that if smaller processors have to wait for a larger amount of time for the CPU, in that case the system will be having larger waiting times. Same as what is happening over here. Actually, P0 got the access of CPU first, and P1 got the access only after P0 has completed. P0 needed CPU for 100 milliseconds, whereas P1 needed CPU only for 2 milliseconds. But for those 2 milliseconds, it was there in the waiting state for 100 milliseconds. This is where it has put the impact, and that is why the waiting time was on the higher side. So what is the answer to this problem? So obviously in that case, it is better to execute smaller processes than the larger processes, so that the average waiting time comes out to be on the lower side. So this is what I have been tried over here in this. The process with smaller burst time was given the access of CPU first, and thereafter the process which needed CPU for larger amount of time was given the access of CPU. And the results are in front of us. That is the CPU, that is the average waiting time in this scenario, comes out to be on the lower side. So let's move on to the next slide, where we'll be discussing about the pros and cons of FCFS. Now, as far as pros and cons of FCFS are concerned, obviously, the very first advantage of this FCFS is that it is quite simple and it is quite easy to understand. Why it is so? Because simply we are taking the processes and allocating to the CPU in the order in which they are entering into the ready queue. It is irrespective of whether the processes that are waiting in the queue are having higher priority, or some quantum is over there set for this, that is they are time share. Like in time shared system, the processes usually get CPU for equal amount of time, but no such things happens over here. The one who enters the queue first gets the CPU at the very first time, at the very first stage, and thereafter the subsequent processes which are waiting in the queue get the access of the CPU. Now, uh, because of this, because once the process gets a CPU, so it basically holds the control of CPU with itself for its entire burst period. But if we compare it with other algorithms, their processes need to go for multiple context switches, and we have read that context switches basically is just an overhead. So because there are low number of context switches, that is why the overheads are also on the lower side. So low scheduling overhead results in context switches are resulted because the context switches are less in this case. Now, if we talk about the negatives of FCFS, basically what happens over here is smaller processes might have to wait for larger period of time in case some processes are having burst times which are more quite high, that is they are CPU bound processes. So this may lead to a convoy effect kind of thing, and the impact of the convoy effect is that the average waiting time for such a system will be on the larger side. The second thing is FCFS is non-preemptive, which means that once a process gains the access of CPU forcefully, the control cannot be taken back from that process for CPU and can be given to the other processes. So in case the system is a time shared system, so in that case each process is not able to gain access of CPU at regular interval. As we know that in time shared systems, each process gets the access of CPU for a certain period of time on turn by turn basis. But over here, basically, there is no such scenario. Once the process gains the access of CPU, it will continue with it for its entire burst period. So that is why in time shared system, the processes are not able to gain access of CPU at regular intervals. So that's all about FCFS. So in the next video, now we'll be discussing about the shortest scheduling algorithms. So till then, I hope that you must have got an idea of how FCFS works. Thank you.